The 1930s were a period of massive consolidation in classical physics. But in the world of electrical engineering, there was a figure who seemed to be speaking a language no one else understood. Gabriel Kron was a scientist and engineer who looked at a simple electric motor and didn't just see wires and coils, but a complex geometrical landscape, a non-Riemannian space where forces moved like planets in orbit. This wasn't just a metaphor for him. He developed a unified theory that treated all machines as specific cases of a single generalized model, using the heavy mathematical machinery of tensor analysis and algebraic topology. It's a story of a man who was decades ahead of his time, often misunderstood and even vilified by his peers. Yet he received encouragement from no less than Albert Einstein and John von Neumann. We're exploring the life and the incredibly dense, almost prophetic engineering philosophy of Gabriel Kron.
It's fascinating because Kron didn't come from the traditional centers of academic power. He was born in a small town in the Carpathians in what was then Hungary and is now Romania. He was the eighth child, and from a very young age, he had this almost obsessive drive for knowledge. He'd spend his days teaching, then pivot to hours of stenography, algebra, French, and physics, often working until 10 at night. When he eventually made it to the United States in 1921, he and his brother arrived with almost nothing. He worked as a dishwasher while studying at the University of Michigan, but his mind was already wandering into cosmology and the fundamental structure of the universe. He actually wrote a paper called Fundamentals of New Cosmology while still a student, where he tried to view the entire universe through the lens of an engineer. He was already disregarding the standard constraints of relativity and gravitation to see if there was a more structural, interconnected way to describe reality.
That rebellious streak seems to define his whole career. After he graduated, he didn't just take a desk job. He went on this incredible journey around the world with just a textbook on differential equations in his bag. He's walking through the Australian outback and the streets of Saigon, and he's seeing these parallels between the maps he's using and the engineering systems he'd studied. He starts to think of a bridge or an airplane not as a static object, but as a network of spaces connected by roads of physical laws. That's a very abstract way to look at a motor. Most engineers at the time were focused on the practicalities of copper and iron. How did that transition from a philosophical walkabout into the rigorous, controversial mathematics he's known for?
It happened because he realized that the connectivity he was seeing, the way parts influence each other through a shared structure, had a mathematical name: tensor analysis. Tensors are essentially mathematical objects that describe linear relations between other objects. The beauty of a tensor is that it's invariant. If you change your coordinate system, the components of the tensor change in a very specific way so that the underlying physical reality remains the same. Kron realized that if you treat an electrical network as a geometric space, you can use tensors to describe how the system behaves regardless of how you map it. In 1930, he published Generalized Theory of Electric Machinery, which was the first shot in a long war. He argued that every electric machine, whether it's a DC motor or a complex alternator, is just a special case of one primitive machine. If you understand the primitive, you can derive any other machine just by changing the coordinate system or the way the parts are connected.
That sounds like an incredible labor-saving device for an engineer, yet the response was apparently quite hostile. Why did the engineering community push back so hard? If it's a way to simplify thousands of different designs into one framework, you'd think they'd embrace it.
There were two main barriers. First, the math was just too dense. Most engineers in the 30s weren't trained in tensor calculus or non-Riemannian geometry. They saw it as an undeserved impression on people who didn't know the math, as one critic in the journal Elektrичество put it. They thought he was being needlessly complex for the sake of it. The second issue was that Kron's intuitions often outpaced his formal proofs. He'd jump to these brilliant conclusions using engineering feel, and pure mathematicians were horrified by his lack of rigor. He was mixing electrotechnical jargon with high-level physics in the way that left both groups feeling alienated. But while the engineers were scoffing, the heavy hitters in physics were paying attention. Benesch Hoffmann, who worked with Einstein, was a huge supporter. Einstein himself reportedly told Kron that he knew of his work because his collaborators were using Kron's non-Riemannian dynamics to solve practical problems in the general theory of electric and gravitational fields. Think about that. The man reinventing our understanding of gravity was looking at an electrical engineer's work on motors for inspiration.
It's a classic case of being caught between worlds. He's too mathematical for the engineers and too much of an engineer for the mathematicians. But let's dig into this non-Riemannian geometric space part, because that's a heavy term. Usually, we hear about Riemannian geometry in the context of general relativity, the idea that space is curved. What does it mean for an electric motor to be non-Riemannian?
This is where Kron really showed his genius. He used the Lagrange equations of motion, which are standard for describing dynamic systems, but he realized that for electrical machines, you have these non-holonomic constraints. In simple terms, that means the system's state depends on the path it took to get there, not just its current position. In geometry, if you move a vector around a closed loop in a curved space and it doesn't return to its original orientation, that's curvature. Kron found that in electrical machines, the interaction of magnetic and mechanical forces created a kind of torsion in the mathematical space representing the machine. To account for this, he had to move beyond the standard curved geometry of Riemann and into non-Riemannian spaces that allow for this torsion. He successfully showed that the nuisances of these complex electrical axes could be treated as the motor moving through this exotic geometric space. It earned him the Montefiore Prize from the University of Liège in 1935, which is a massive deal in the field.
So he's building this massive, unified theory, but then the world changes. We get into the era of big systems, power grids, complex aircraft, and eventually computers. This is where he introduces diacoptics, which sounds like a medical procedure, but is actually a strategy for solving massive problems. How does that work?
Diacoptics comes from the Greek word diakopto, which means to tear apart. It was Kron's answer to the problem of scale. Even today, if you have a system with thousands of variables, like a national power grid, calculating how everything interacts at once is computationally expensive. Kron's idea was, why not tear the system into smaller, isolated subsystems? You solve each small part independently, and then you use tensors to sew the solutions back together. The magic is in the tensor of joint. This tensor describes the connections between the pieces. Because you've already solved the internal logic of each part, the final step is just a transformation that accounts for how they're interconnected. He showed that this could save an enormous amount of time. If you tear a system into n parts, the time saved in matrix manipulation is roughly proportional to n squared. It was a precursor to modern parallel processing and distributed computing.
It feels like he was building a toolkit for a computer that hadn't been invented yet. He's working at General Electric for decades, doing this deep theory, but then toward the end of his life, things get even stranger. He starts talking about self-organizing polyhedral networks and wave machines. This sounds less like power engineering and more like early AI or even biology.
Exactly. In his final decade, Kron was obsessed with what he called the crystalline computer. He started looking at multi-dimensional spaces, not just points and lines, but planes, cubes, and higher dimensional simplexes, and connecting them into a structure called a polyhedron. He believed that these networks could hold much more information than a simple set of equations because they represent the environment around every point, not just the point itself. He envisioned these as self-organizing automata that could oscillate at any frequency. He even proposed that an electromagnetic wave could spread through these networks in a way that satisfies Stokes' theorem, provided you have two dual polyhedrons, one made of magnetic material and one dielectric. He was essentially trying to build a mathematical model of an artificial brain, where each neuron was a generalized rotating electric machine. He called it a dynamo-type automate.
That's a huge leap. He's moving from how do we build a better generator to how do we model consciousness or universal order. It reminds me of the work by Ilya Prigozhin on order from chaos. Was Kron trying to find a way to let a system organize itself mathematically?
There's a direct conceptual link there. Prigozhin, who won the Nobel Prize, showed how open systems far from equilibrium can spontaneously organize themselves. Kron's adaptive polyhedrons were designed to do something similar in a mathematical sense. They could take chaotic, multidimensional data and, quote-unquote, automatically organize it into a solution space by adjusting their own internal parameters, their waves, to match the boundary conditions. He demonstrated this by simulating complex
complex functions using a model of 13 interconnected generalized machines. The accuracy was staggering. He wasn't just solving a problem, he was creating a system that could adapt to any problem of that type without changing its internal structure. He even suggested this could be used for tensor databases, where you could transition from one set of information to another just by applying a transformation rule, rather than searching from scratch every time.
It's almost heartbreaking to think that he was doing this in the 50s and 60s when the hardware couldn't even begin to touch these ideas. He's talking about regulated chaos and fractals before those terms were even in the mainstream. Does his work live on in modern engineering, or is he one of those figures who just drifted into the folklore of the field?
It's a bit of both. In Russia, there was a significant effort to translate his work in the 70s and 80s, particularly by scientists like A.E. Petrov, who saw the value of tensor methodology in systems theory. Today, Kron reduction is a standard technique in circuit theory and power systems for simplifying complex networks. Diacoptics is still used in large-scale simulations, like shipboard power systems or nuclear reactor controls. But his more out-there ideas, the polyhedral wave machines and the magnetohydrodynamic plasma models for the brain, those remain largely unexplored. They sit on the edge of what we're currently doing with neural networks and categorical systems theory. There's a sense among those who study his heritage that we've only scratched the surface. Kron wasn't just an engineer, he was a universal engineer who believed that the laws of the universe were interconnected in a way that a single, elegant mathematical language could describe.
He seems to have lived in a state of constant intellectual tension. He was a pioneer who was appreciated by only a few during his life, yet he never stopped. He even worked until his retirement at 65 at General Electric, and until his death in 1968, he believed his greatest achievements were still ahead of him. He looked at the world as a network of spaces, and in a way, he was the bridge between the classical world of steam turbines and the future world of adaptive, self-organizing intelligence. His story is a reminder that sometimes the most useless and overly complicated theories are just the ones that haven't found their era yet.
He really was the quintessential outsider. Whether it was teaching himself languages while walking 14 miles a day as a teenager, or challenging the greatest engineers of his time with non-Riemannian geometry, he refused to accept that there were limits to what a single mind could unify. He saw beauty in the tensors, in the way they protected the objective essence of a system from the arbitrary ways we choose to measure it. To him, a machine wasn't a collection of parts. It was a physical manifestation of a geometric truth. And while his nomenclature might have been grounded in electrical engineering, his vision was truly universal.
It's a legacy that encourages us to look for those hidden connections in our own fields, to see the roads and laws that turn a collection of details into a unified whole.
In the early 1960s, a man named Gabriel Kron walked the 4 miles from the General Electric Research Labs in Schenectady, New York, to his home every single evening. He was 60 years old, a legend in electrical engineering, and he was deeply obsessed with a vision that his colleagues could barely grasp. While the rest of the world was just beginning to toy with the idea of simple digital logic, Kron was sketching out something far more radical: an artificial brain built not of transistors and code, but of oscillating electromagnetic waves flowing through multidimensional polyhedral structures. He called them self-organizing wave automata, and he believed they were the crowning achievement of his career. To understand why Kron thought a geometric shape could model the human mind, we have to look at the man himself. Gabriel Kron was never a conventional thinker. Born in Transylvania at the turn of the century, he arrived in the United States with nothing but a math book and a suitcase. He spent his youth literal-mindedly walking across the globe, trekking through the deserts of North Africa and the mountains of India, using the physical movement of his body to fuel his mathematical intuition. By the time he landed at GE in 1934, he had already pioneered diacoptics, a method of tearing complex systems into smaller pieces to solve them separately and then sewing them back together with tensors. This wasn't just math to him. It was a philosophy of how the universe functioned. Kron saw the world as a network of interconnected physical essences, where every rotating machine, every power grid, and every biological organ was just a specific case of a single generalized theory. But in his final decade, Kron's work took a turn into the truly strange. He moved away from the stable, linear world of power lines and began to investigate the chaotic, nonlinear behavior of what he called polyhedral networks. Imagine a network not just as lines on a flat page, but as a three-dimensional lattice of cubes or even higher dimensional shapes like simplexes. In Kron's model, these weren't just static frames. He envisioned them as being filled with a moving plasma, a magneto-hydrodynamic fluid that allowed waves of energy to propagate through the structure. He argued that these waves would interact and self-organize, much like the pulsing electrical signals in a human brain. He wasn't interested in the switching logic of modern computers. He wanted to capture the fluid, energetic nature of consciousness itself. This wasn't just a theoretical exercise. Kron claimed to have built a physical prototype he called the crystal computer, a small device he supposedly carried in his pocket that could solve complex nonlinear equations by allowing waves to flow through a crystalline structure. He described it as a vest pocket computer, a phrase that sounds eerily like a smartphone today, but his technology was fundamentally different. He believed that by tuning the frequencies of these waves, the polyhedral automaton could perform what he called image recognition and form-fitting, decades before those became standard terms in machine learning. He saw the polyhedron not just as a box of parts, but as a dynamic entity that could reach an equilibrium state, essentially learning the structure of the data it was processing. The controversy surrounding Kron was intense. His papers were published in respectable journals like Matrix and Tensor Quarterly, but many of his peers thought he had simply gone off the rails. He used language that sounded more like a mystic than an engineer, talking about non-Riemannian dynamics and unified field theories applied to simple circuits. Mathematicians accused him of a lack of rigor, while engineers found his multidimensional tensors impossible to follow. Yet, when you look at his work today, the parallels to modern neural networks are startling. We now use tensors to build the very foundations of deep learning, and we rely on the same piecewise logic of diacoptics to train massive models across thousands of processors. Kron's wave automata may have been a physical metaphor for what we now do with digital code, but his core insight that intelligence emerges from the complex, self-organizing interactions within a multidimensional network was remarkably prescient. Gabriel Kron died in 1968, and his mysterious crystal computer vanished with him. He left behind a legacy that is part engineering genius and part science fiction, a reminder of a time when the path to the artificial brain was still an open, unpaved road. In the early spring of 1968, a man named Gabriel Kron was nearing the end of a long, strange journey. To his colleagues at General Electric in Schenectady, New York, he was a brilliant, if eccentric, staff engineer, a pioneer of tensor analysis who had spent decades simplifying the world's most complex power grids. But in his private hours, he was chasing something far more elusive. He called it a wave automaton, or sometimes with a touch of protective irony, his vest pocket computer. It wasn't a computer in the sense we know it today, with silicon chips and binary code. It was a physical machine, a geometric AI built from crystals in copper, designed to think not through logic, but through the movement of electromagnetic waves. For years, rumors have swirled that Kron actually finished it, a device the size of a cigarette pack that could solve problems beyond the reach of the era's room-sized mainframes. But when he died that March, the machine seemingly vanished. Today, we look at the final years of an inventor who believed the universe itself was a giant crystal and the search for the physical AI he might have left behind. To understand the machine, you have to understand the man's history. Gabriel Kron didn't start in a lab. He started on a dirt road. In 1924, after graduating from the University of Michigan, he didn't take a job. Instead, he spent 2 years walking around the world with nothing but a backpack and a math textbook. He hiked through the Australian outback and trekked across Southeast Asia. And it was during these long, solitary walks, but he had a revelation. He realized that a machine, whether it was a bridge, a turbine, or a power line, wasn't just a collection of parts. It was a mathematical space. He saw engineering structures as imaginary maps of unknown territories, interconnected multidimensional spaces linked by a web of laws. When he finally returned to the U.S. and joined General Electric in 1934, he brought this vision with him. He treated electrical networks as dynamic systems living in non-Riemannian spaces, a level of abstraction that left most of his peers baffled. He was often shuffled from department to department, tasked with solving the impossible problems of steam turbines or nuclear reactor controls, because his mind didn't follow the standard rules of engineering. By the 1960s, Kron's focus had shifted toward the wave automaton. This wasn't just another circuit. It was an attempt to build a self-organizing brain. The technical heart of this project was something called diacoptics, or the method of tearing. Kron's insight was that you could solve a massive, complex system by literally tearing it apart into smaller, independent pieces, solving those, and then stitching them back together using the geometry of the connections. But the wave automaton went a step further. Kron envisioned a network of magneto-hydrodynamic generators, generalized rotating machines acting as neurons. He used polyhedral structures, complex three-dimensional shapes, to house these networks. The mechanics were based on a specific, verified claim that an electromagnetic wave traveling through a polyhedron could be made to interact with itself in such a way that the network would organize its own path. He believed that even-dimensional spaces were made of magnetic material, and odd-dimensional spaces were dielectric. By alternating these layers, he created a physical environment where energy could find its own equilibrium, effectively learning the solution to a problem as a wave passed through it. The legendary vest pocket version of this machine was his prototype. According to accounts from his close associates, like the mathematician Bonnesh Hoffman and the engineer Philip Alger, Kron's crystal computer utilized the simultaneous activity of a crystal under the stimulation of a single electric source. He drew a direct analogy between the way light scatters through a crystal and the way an electromagnetic field moves around a current. By using topology, the math of shapes, he claimed he could manipulate these waves to perform calculations at speeds that made digital computers look like toys. In his final years, he grew increasingly secretive about the device. He told friends he had proof of its superiority, but refused to publish the full details, fearing his work would be misunderstood or plagiarized before he could perfect it. This secrecy was fueled by a long-standing conflict with the scientific establishment. Kron had a history of discovering things the textbook said were impossible, like true negative resistor, a circuit that could theoretically power itself by drawing energy from its environment. He reportedly demonstrated this negative resistor to the U.S. Navy at Stanford, but the results were never openly discussed, leading to whispers of a long-suppressed discovery. As Kron's health began to fail in early 1968, he became obsessed with a general theory of the universe. He started to view the entire cosmos as a giant, self-organizing crystal, a system where every point was connected to every other through open paths that defied traditional physics. He spoke of shortcuts for travel between planets and suggested that his wave automaton was just a small-scale model of how the universe actually functions. But on March 25th, after a short illness, Gabriel Kron passed away in Schenectady. In the wake of his death, the search for the physical AI began. His colleagues, H. Happ and others at GE, spent years trying to decipher his last papers, but they found them incredibly dense, written in a style more like a soothsayer than a scientist. The physical prototype, the vest pocket machine that could supposedly think with waves, was nowhere to be found. Some believe it was reclaimed by General Electric or the Navy. Others think Kron might have destroyed it himself, realizing the world wasn't ready for a machine that bridged the gap between engineering and the infinite. The legacy of Gabriel Kron lives on in the math. His diopchondrics and tensor methods are now foundational to modern power systems and the domain decomposition used in supercomputing. We see his physical AI echoed in today's research into optical computing and neuromorphic chips, which use physical materials to mimic the brain's efficiency. Kron was a man who walked around the world to find a new way to see it, and in doing so, he might have built a machine that saw the world exactly as it was. Whether the vest pocket automaton still sits in a dusty box in a GE warehouse or was merely a beautiful mathematical dream, it remains a testament to an inventor who refused to accept the boundaries of the possible.
There's a specific, almost eerie property in the way waves move that most of us never think about. If you drop a stone into a perfectly still pond, the ripples don't just move, they calculate. As those circles expand, they're essentially solving an incredibly complex equation in real time, accounting for the density of the water, the force of the impact, and the boundaries of the shore. For a long time, if an engineer wanted to simulate that, they had to rely on massive, crunching calculus, the kind of math that can take a supercomputer days to finish if the shape of the pond is even slightly weird. But there's a different way. It's a concept that feels more like a video game than a textbook, and it's called a wave automaton. It's an idea that suggests that instead of trying to solve the universe's equations from the top down, we can let the universe build itself from the bottom up, using simple, local rules. And when we apply this to multidimensional spaces and the abstract world of topology, we start solving engineering problems that were once considered mathematically impossible. It's a shift from seeing the world as a series of equations to seeing it as a massive, self-correcting grid of information. This is where math meets the absolute limit of how we build the future. Part 1. The Ghost in the Grid. To understand why wave automatons are so revolutionary, we have to look at the man who championed the idea that the universe itself might just be a giant computer, Edward Fredkin. In the 1980s, Fredkin proposed a hypothesis called finite nature. He argued that at the very bottom of reality, smaller than atoms, smaller than quarks, everything is discrete. It's not a smooth, continuous flow. It's grainy. It's digital. Think of it like a digital photo. From a distance, the colors bleed into each other perfectly, but zoom in far enough and you're staring at individual pixels. Fredkin's big leap was suggesting that space and time are the same way. If space is made of cells and time moves in ticks, then the laws of physics aren't these mystical overarching forces, they're just the rules of the grid. This brings us to cellular automata. You might have seen John Conway's Game of Life. It's a simple grid where cells live or die based on how many neighbors they have. It looks like a toy, but it's actually a universal computer. A wave automaton is a specialized version of this. Instead of cells just being on or off, each cell contains a small bit of information about wave intensity and velocity. In a traditional engineering simulation, if you want to know how a sound wave travels through a car engine, you use something called finite element analysis. You're basically trying to solve a global equation for the whole system at once. It's like trying to choreograph a dance for 10,000 people by giving every single person a copy of the entire 500-page script. It's slow, and if one person trips, the whole math falls apart. But a wave automaton works like a flash mob. There's no master script. Each person just looks at the two people next to them and follows one simple rule. If the person on my left raises their hand, I wait 1 second and then raise mine. When you step back, a perfect wave ripples through the crowd. This is locality, the idea that the big picture emerges from tiny local interactions. It's incredibly efficient because the computer doesn't have to keep track of the whole wave. It only has to keep track of what each individual cell is doing right now. This shift allowed engineers to start modeling things that were previously too complex to touch, like how a tsunami interacts with the jagged, unpredictable coastline of an entire archipelago, or how a crack spreads through a microscopic piece of experimental alloy. Part 2. Thinking in higher dimensions. Now, things get really interesting when we stop thinking about 2D grids and start pushing into multi-dimensional spaces. In standard engineering, we live in 3 dimensions, height, width, and depth. But in the math used by people like Robert Grist at the University of Pennsylvania, a dimension is just a piece of information. If you're tracking a single robot on a factory floor, you need 2 dimensions, X and Y. If you have 2 robots, you need 4. If you have 100 robots, you're suddenly working in a 200-dimensional space. We can't visualize a 200D world, but the math of wave automatons doesn't care. It treats those dimensions as just more neighbors in the grid. This leads us to the concept of topology. In common language, we think of geometry as the study of shapes, how long a line is or the angle of a corner. Topology is different. It's often called rubber sheet geometry. It's the study of properties that don't change even when you stretch or twist an object. To a topologist, a coffee mug and a donut are the exact same thing because they both have one hole. You could theoretically mold the clay of a mug into a donut without ever tearing it or gluing pieces together. Why does this matter for waves? Because when waves travel through complex structures, like the power grid of a major city or the internal lattice of a 3D printed jet engine part, the shape of the space they're moving through changes their behavior. By using wave automatons in these abstract topological spaces, engineers can find holes in a system that they couldn't see before. For example, in a massive sensor network, you might have thousands of little devices covering a forest. How do you know for sure there isn't a dead zone where a fire could start undetected? Traditional math would struggle to map every inch of that uneven terrain. But a topological wave automaton can flow through the network's data. If the wave gets stuck or circles back on itself in a specific way, the math reveals a hole in the coverage, regardless of how messy the physical forest is. It turns a nightmare of coordinates into a simple question of connectivity. Part 3. Solving the impossible engineering problems. This brings us to the actual impossible engineering problems being solved today. One of the most cutting-edge fields is something called topology optimization. Imagine you're designing a bridge. Usually, you'd start with a big block of steel and carve away what you don't need, or you'd use standard beams. But with a wave automaton, you can do the opposite. You define where the weight is going to be and where the supports are, and then you let a digital wave of material grow into the space. The automaton follows a rule. If there's a lot of stress here, add more material. If there's none, remove it. The result isn't a bridge that looks like anything a human would design. It looks organic, like bone or the roots of a tree. It's lighter, stronger, and uses half the material. This is also how we're developing metamaterials, substances engineered at the microscopic level to have properties that don't exist in nature. There are materials designed using these wave-based rules that can actually bend sound waves around an object, making it acoustically invisible. It's a literal invisibility cloak for sound. Another area where this is huge is in structural health monitoring. Scientists are using wave automatons to model Lamb waves. These are complex waves that wrap around the surface of thin plates, like the skin of an airplane wing. When a tiny, invisible crack forms inside the metal, it changes the way those waves flow. By running a wave automaton simulation in parallel with sensors on the actual plane, engineers can detect a microscopic fracture long before a human inspector could ever see it. They're essentially using the local rules of the material's own vibrations to tell them when the global structure is failing. It's a leap from reactive maintenance, fixing things when they break, to what's called prognostics, where the math tells you exactly when and where a failure will happen weeks in advance. It's the difference between guessing where the ripples will go and knowing the destination the moment the stone hits the water. Part 4. The Legacy of the Discrete. Looking back, the journey from Fredkin's finite nature to the engine rooms of modern aerospace is a story about the power of simplicity. We spent centuries trying to master the infinite. Calculus, continuous curves, the idea that you can always divide space into smaller and smaller pieces. And that math got us to the moon. But it turns out that when things get truly complex, when we're talking about billions of interactions in a power grid or the chaotic flow of a tsunami, the infinite becomes a wall. It's too heavy. By embracing the discrete, by accepting that maybe the world is just a grid of tiny local decisions, we've found a shortcut. Wave automatons aren't just a trick for faster computing. They're a fundamental insight into how complexity actually works. They suggest that the most difficult problems in the world don't need a genius at the top with a master plan. They need a system at the bottom with the right rules. Whether we're designing more efficient wind turbines through AI-driven design iterations or creating topological insulators that could revolutionize quantum computing, we're essentially learning to speak the language of the ripples. We're moving toward a future where our buildings, our machines, and even our cities aren't just static objects, but mechanically intelligent structures that can perceive, decide, and respond. It's a world where the math doesn't just describe reality, it is reality. And as we continue to map these multidimensional spaces and push the boundaries of what topology can teach us, we might find that the impossible was just a matter of looking at the grid from the wrong angle.
Imagine a vast, infinite grid of squares, like a sheet of graph paper stretching out in every direction. Each square can only be one of two things, black or white, alive or dead. There are no physical forces, no gravity, and no atoms. There are only three simple rules that dictate whether a square stays alive, dies, or is born from the void. On the surface, it sounds like a children's game or a trivial mathematical exercise. But within this tiny, two-dimensional universe, something incredible happens. Patterns emerge that look like organic life. They move, they reproduce, and they even perform complex calculations. This is the world of cellular automata, a concept that has challenged our understanding of biology, physics, and the very nature of reality since the mid-20th century. Imagine a vast, infinite grid of squares, like a sheet of graph paper stretching out in every direction. Each square can only be one of two things, black or white, alive or dead. There are no physical forces, no gravity, and no atoms. There are only three simple rules that dictate whether a square stays alive, dies, or is born from the void. On the surface, it sounds like a children's game or a trivial mathematical exercise. But within this tiny, two-dimensional universe, something incredible happens. Patterns emerge that look like organic life. They move, they reproduce, and they even perform complex calculations. This is the world of cellular automata, a concept that has challenged our understanding of biology, physics, and the very nature of reality since the mid-20th century.
The most famous version of this is the game of life, created by the mathematician John Conway in 1970. It is often cited as the ultimate example of emergence, where complex global behavior arises from simple local rules. The rules Conway settled on are remarkably elegant. First, any live cell with fewer than two neighbors dies, as if by solitude. Second, any live cell with two or three neighbors lives on to the next generation. Third, any live cell with more than three neighbors dies, as if by overpopulation. Finally, any dead cell with exactly three live neighbors becomes a live cell representing birth. These rules were the result of months of experimentation because Conway wanted to find a balance where the system didn't just collapse into static patterns or explode into chaotic noise.
But it is fascinating that he had to hunt for that balance. It suggests that complexity is a rare state, a thin line between total order and total chaos. If the rules were just slightly different, say, if 4 neighbors were required for birth instead of 3, the entire system might stay dark forever. But because he found this specific sweet spot, the game of life became a sensation. When Martin Gardner first wrote about it in his mathematical games column for Scientific American in October 1970, it reportedly caused a massive drain on the world's computing resources because so many researchers and students were running simulations on their university mainframes.
Gardner's column really was the spark, but the intellectual roots go back much further, specifically to the 1940s and the work of John von Neumann. At the time, von Neumann was obsessed with the idea of self-replicating machines. He wanted to know if it was theoretically possible to build a machine that could build a copy of itself. Stanislaw Ulam suggested that instead of trying to design a physical robot with gears and motors, he should look at a discrete system on a grid. Ulam's background in crystal growth led him to think about how patterns expand based on the state of their neighbors. This shift from physical hardware to mathematical logic birthed the field of cellular automata.
Von Neumann's original model was much more complex than Conway's. I believe it involved 29 different states for each cell, which makes Conway's two-state system look like a miracle of simplification. But the goal was the same, to show that simple rules could lead to universal construction. If we look at what actually happens on the grid in Conway's version, we see these distinct species of patterns. There are still lifes that never change, like a simple 2x2 square. Then there are oscillators that flip-flop between two states, but the real stars are the spaceships.
The glider is the most iconic spaceship. It's a small cluster of 5 cells that, through the rules of birth and death, shifts itself diagonally across the grid. It looks like it's walking. When people first saw this, it changed the conversation from mathematics to something that felt biological. It showed that motion in a discrete universe isn't a fundamental property, it's an emergent property. The cells themselves aren't moving. A cell just turns on or off. The pattern is what moves. This distinction is vital because it mirrors how we think about particles in physics. An electron might just be a localized excitation in a field, much like a glider is a localized excitation on a grid.
That analogy to physics is provocative, but there's an even deeper layer here regarding computation. We often hear that the game of life is Turing complete. To the average person, that sounds like academic jargon, but the implications are profound. It means that if you have a large enough grid and the right initial configuration, you can build a fully functional computer inside the game of life. You can create logic gates and, or not, using gliders as signals. If two gliders collide in a certain way, they might annihilate each other or produce a new glider which functions exactly like a transistor switching a signal.
It's been proven that you can build a universal Turing machine within this two-state grid. In fact, people have built versions of the game of life inside the game of life. They've constructed massive patterns that act as metacells. When the large pattern is on, it goes through a cycle that mimics the rules of the smaller cells. This demonstrates that there is no limit to the level of complexity you can stack. If you can build a computer, you can simulate any physical process that is computable. This brings up the controversial idea proposed by Edward Fredkin and later championed by Stephen Wolfram that the universe itself might be a cellular automaton at the Planck scale.
Wolfram's work in the 1980s and his massive 2002 book, A New Kind of Science, took this in a different direction by moving away from Conway's two-dimensional grid and looking at even simpler one-dimensional systems. In these, a single row of cells evolves into a second row based on the states of the neighbors above it. Even with these even more restricted systems, he found what he called Rule 30. Despite starting from a single black cell and following a perfectly deterministic, simple rule, the pattern it produces is so chaotic that it passes many tests for mathematical randomness. This creates a bridge between simple determinism and the kind of chaos we see in weather patterns or fluid dynamics.
Rule 30 is a perfect example of computational irreducibility. In traditional physics, we use equations to predict the future. If I throw a ball, I can use a formula to tell you where it will be in 5 seconds without having to simulate every millisecond of its flight. But with Rule 30 and many cellular automata, there is no shortcut. To find out what the 1,000th row looks like, you have to run the simulation for all 999 rows. You cannot outrun the system. This challenges the Newtonian view that the universe is a clockwork mechanism we can fully predict if we just have better math. It suggests that some processes are their own fastest simulation.
Wolfram categorized these automata into 4 classes, which I find very helpful for understanding why some systems are boring and others are alive. Class 1 disappears or becomes a solid block. Class 2 settles into repetitive, predictable patterns. Class 3 is pure chaos, like Rule 30. But Class 4 is where the game of life sits. It's where you get long-lived, complex structures that interact in non-trivial ways. Class 4 is the edge of chaos. If a system is too ordered, it can't process information because nothing ever changes. If it's too chaotic, information is destroyed by noise. Life and computation seem to require that precarious balance found in Class 4.
This has practical applications far beyond theoretical math. Biologists use cellular automata to model the patterns on seashells, like the Conus kextile, which looks remarkably like Rule 30. The growth of crystals, the spread of forest fires, and even the way traffic jams form on a highway are often modeled using these systems. In a traffic model, each car is a cell. The rules are simple. If there's space in front, move forward. If there's a car in front, stop. These simple interactions recreate the strange phantom traffic jams that happen for no apparent reason. It turns out that the macro-scale problem of a traffic jam is just an emergent property of the micro-scale rules of individual drivers.
We should also talk about the philosophical tension here. On one hand, cellular automata suggest that the most complex things in the world, consciousness, the weather, the economy, might actually have very simple underlying rules. It's a reductive dream. But on the other hand, because of computational irreducibility, knowing those rules doesn't actually give us the power to control or predict the outcome. It's a weird paradox. The rules are simple, but the behavior is infinite and unpredictable. Does this imply that our own sense of free will might just be the result of being a Class 4 system that is too complex to predict its own next state?
That is the central debate. If you subscribe to the digital physics view, you're essentially saying that at the very bottom of reality, there's no smooth space or time, just bits being processed. Critics, however, point out that cellular automata are usually discrete and rely on a fixed grid, whereas our best theories of physics, like general relativity, rely on continuous, smooth manifolds. There's a massive gap between a grid of squares and the curved spacetime described by Einstein. However, researchers like Stephen Wolfram and others are working on hypergraph models that try to bridge this gap, showing how a discrete network can look like smooth space when viewed from a distance.
It's also worth noting the cultural impact. The game of life wasn't just a math hobby. It influenced how we think about artificial life. It prompted the question of whether something has to be made of carbon to be considered alive or intelligent. If a pattern in a computer can move, react to its environment, reproduce, and even think, if it's a computer itself, at what point do we stop calling it a simulation and start calling it a life form? Conway himself was often surprised by how people fixated on this.
Conway actually had a bit of a love-hate relationship with the game of life later in his career because he felt it overshadowed his more serious mathematical work, like his discovery of the Conway groups and symmetry. But its legacy is undeniable. It showed us that complexity isn't the opposite of simplicity, it's the result of it. When we look at the jagged edges of a snowflake or the branching of a river, we don't need to invoke a complex blueprint. We only need to find the simple, iterative rule that the system follows. This realization has shifted the focus in many scientific fields from searching for laws to searching for algorithms.
There's a certain beauty in the idea that the universe doesn't need to be complicated to produce complexity. It just needs to be persistent. If you let these simple rules run long enough on a large enough scale, you get us. You get people sitting in a room talking about the rules. It's a self-referential loop that is almost poetic. We are the class 4 patterns that have become complex enough to look back at the grid and try to figure out the code we're running on.
And this search continues. Today, researchers are using quantum cellular automata to explore how these principles work in the quantum realm. Others are using them to design new materials or to understand how the brain processes information through local interactions of neurons. The 3 rules of birth and death were just the beginning. They opened a door to a way of seeing the world where the most profound truths aren't hidden in giant equations, but are visible in the tiny, repeating steps of a simple process. It reminds us that we should never underestimate the power of a simple starting point.
The sheer scale of what has been built within the game of life is a testament to this. There is a project called Life in Life, where they built a version of the game of life grid, where each cell is actually a 2048 by 2048 pixel pattern of gliders and eaters that mimics the rules. This goes on for several layers. It's like a fractal of computation. Every time you zoom out, you find the same rules operating at a higher level of organization. It makes you wonder if our own laws of chemistry and biology are just the high-level glider patterns of some even simpler rule beneath them that we haven't discovered yet.
It's a humbling thought. It suggests that while we feel like the protagonists of the story, we might just be the emergent noise of a very long-running program. But regardless of the metaphysical implications, cellular automata remain one of our most powerful tools for exploring the unknown. They provide a laboratory where we can grow universes for the price of a few lines of code, and watch as they evolve, thrive, and eventually dissipate into the void. It is a reminder that the boundary between the artificial and the natural is much thinner than we often like to believe.
What started as a mathematician playing with a grid on a coffee break has turned into a fundamental pillar of complexity science. It shows that even in a world governed by strict, unyielding rules, there is still room for the unexpected and the beautiful. The hidden power of these systems lies in their ability to surprise us, proving that the whole is truly greater than the sum of its parts.